So good morning, good afternoon, good evening, depends on where you are in the world. So thank you very much for joining us today for this another very exciting talk that will be done by Dr. Erika Covi. But today we are here to listen to Erika Covi from NaMLab, Germany. So Erika Covi is a group leader at the NaMLab in Germany, in Dresden. She received the PhD in microelectronics in 2014 from the University of Pavia in Italy, where she worked on designing integrated systems for the characterization of memoristive devices. Before joining NaMLab, she worked at the National Research Council of Italy first, then at Politecnico di Milano, always in national or European projects dealing with the implementation of a neuromorphic-memristive system. She won an ERC starting grant on memristive neurons and synapses for neuromorphic edge computing in 2021. She serves in the board of governance of the IEEE Sequencing Systems Society for the term 2022-24. Her research interests lie at the intersection of emerging devices, circuit design, and brain-inspired computing. More especially, they focus on exploring the intrinsic physical characteristics of memoristive devices to reproduce computational primitives of the brain in mixed neuromorphic memoristive system. So thank you very much, Erika, to accept our invitation. It's a pleasure to have you here. Then I give the floor to you to start your presentation. But before that, I just like to remember everybody that you can put your questions in the YouTube chat channel, and the questions will be read to Erika by the end of her talk. So, Erika, the floor is with you.
Thank you, Ricardo, also for this opportunity. I'm really honored. So, welcome everybody, and good morning, good afternoon, good evening, depending on where you are in the world. So today I want to speak with you about what I do, what I research, because I think it's really an exciting topic, and I would like to share this excitement with you. First of all, I would like to discuss this part, the edge part. Why the edge? So nowadays we have a widespread of artificial intelligence, and we are mainly relying on cloud-based computing. So it means that we have data that are acquired by sensors that we have on our devices. The data are sent to the cloud, where an artificial neural network simulation is run, and the result of the simulation is sent back to our devices. This is a very, very energy expensive process. It has been calculated that in only 3 years, if this trend persists, 20% of the world's electricity will be used for this paradigm. This is not really actually something that we would like, no? Therefore, an idea is, okay, let's move part of the intelligence from the cloud directly to these devices on the edge. And this is what we call edge computing. But as you can imagine, edge computing has some constraints. For example, we do not have the power that we have in the cloud approach. We have less memory than the data center. But we could exploit, for example, this for online learning, so learning while acquiring the data. But all these characteristics mean that we need learning algorithms that can cope with this constraint. For example, for the power, we might need learning algorithms that use few weight updates. Or for the limited memory, we might need a stochasticity to improve the behavior of the network. And anyway, we have to take into account that we have a low bit precision and or few connections because we have also limited area. So what I want to convince you about is that new technologies such as memoristive devices are really useful in this context. And memoristive devices are two-terminal devices which can change their conductance upon application of proper electrical stimuli. And they also have other very interesting characteristics. They can have volatility or non-volatility, which is electrically tunable, and we will see later how it is important. Then we have low power. We have a small footprint, so we can put a lot of them in a small area. They are stochastic, so they help learning algorithms, and they have few bits per device, but this is their feature. Anyway, this is not the whole picture. So the whole picture would be having these systems that put together different aspects directly on the sensor that we are wearing. And that these systems need to be a bridge between the sensors that we're wearing and the application, so why we use them. So today, I want to first befriend memristive technology with you. And especially we'll focus on two technologies, ferroelectric tunnel junctions and resistive random access memory. Then I would like to discuss learning, how we can learn with these devices. So I will start from basic concepts, and then I will show you some examples at neuron on synapse level, or also some example with at the network level. So let's start befriending our memristive devices. I will focus on two technologies, but there are several technologies, and I want to mention also the phase change memory because it's actually one of the most mature. So these devices actually have a very nice property that their physical change in the physical layer, in the physical material, is the thing that changes their conductance, and that allows you to store information. And if we think about biology, we see that there is a certain similarity, because in biology we have neurons that collect the signal and integrate the signal and transmit a signal through synapses. And how the synapses behave will tell you if two neurons need to be connected and linked together, or if this connection is not that important. So given this similarity, we can see that in the past years, there has been a lot of study on memristive devices to have memristive computing. We have actually two main fields. One is the accelerator, deep learning accelerator. We will not discuss about it, but it's important for me to mention because these are architectures that are thought to speed the processing in deep learning, and they have a very high importance. I will focus on brain-like computing. And this is because it's actually a nice challenge. It's a very interesting challenge because we need to understand the device, not only the physics, but also how to drive it from an electrical point of view in order to build systems, bio-inspired systems. And this is a challenge that is still very, very open, I would say, because it implies a lot of steps from learning, understanding the features of the device, understanding which function can be reproduced with each feature, and then combining this function together in algorithms that can then emulate finally computation. And as you can see, there's a lot. And moreover, we have also different challenges because there is no one size fits all in this memristive realm. We have different challenges. First, physically, so we have device level challenges because we have to cope with the properties of the device that sometimes are useful, sometimes are a bit more challenging. And then we have to embed them in circuits. So it means that we have to make sure that our circuit have the driving capability to drive our devices. And moreover, we have a system level challenges because anyway, what happens inside a network has to be communicated outside, and we need to take data from outside, inside the network. And if you have a look at this graph that compares several technologies, well, we see how true this is. Because, for example, we might have devices that are very nice in terms of retention, that can store data for a long time. But then we look at the endurance, and the endurance is not that great. And similarly, also devices that have a high density, integration density, maybe features low maturity. So it's always a matter of optimization, of challenge. And I firmly believe that we can accept the challenge, and we can also make something meaningful, but only if we look at devices, circuits, and learning algorithms all together, and we develop them together so that each of them help exploiting the characteristics of the other. Let's start then now to get to know ferroelectric tunnel junction better. Ferroelectric tunnel junctions have two metal electrodes, and in between we have a ferroelectric material. By applying a current, a voltage pulse, for example, if we apply a negative voltage, we switch all the domains in a certain direction. And if we apply voltage of opposite polarity, we switch them in the opposite direction. What happens microscopically from an electrical point of view is that depending on how this, on what direction these domains have, when we apply a certain voltage, we can read either a lower current or a higher current. And it's here how we store data. And if we can have a look at better at the physics of the device with these two plots. So for example, we see that when we switch the domains, we have some current peaks. That tells us, okay, yeah, something changed, something switched. And the polarization that we can see here, as you can notice, it changes. And this is what is then electrically reproduced here. Anyway, in this layer, we have not one single domain. We have multiple domains. And when we apply a field, these domains switch, but each of them has a certain switching probability and a certain switching time. And we can actually exploit this feature to have analog programming. That means that we can apply, for example, identical pulses that have same voltage but different time width, or same time width and different voltage, and we can obtain different states. This is a non-linear operation, but it's still multi-level, so it means that it's usable for learning. And also another characteristic here, as you can see in this plot here, is that the current of these devices is very, very low. In fact, ferroelectric tunnel junction, so far, it's the most power-efficient memristive technology. Let's have a look now at resistive switching devices. Here, we have more or less the same structure, but we have an oxide. And when we apply a certain field, we move the vacancies or the impurities in the oxide, and we create a conductive filament. This operation is called forming. Then, if we apply an opposite voltage, we partially disrupt this filament, and then again we are able to restore this filament. And this is the behavior electrically. So we apply a certain voltage, we are in a high resistive state, and then we form the filament and we go in low resistive state. Then we change the voltage, and you see here we are still in low resistive state, but at a certain point the filament partially disrupts and we go back to the high resistive state. This operation is non-volatile. But if we, for example, here choose a certain material, specific material, for example, silver, we have that silver ions migrate in the oxide. But silver is, the mobility of silver is high. So the filament is created, but then as soon as we stop applying any kind of voltage, the filament will slowly start to self-disrupt. And you can see it here, for example, we create the filament, and then the filament dissolves. And when we apply a voltage of the opposite polarity, we start from a low current state, so a high resistive state, and we go back. If we apply a pulse, what happens is this. The current is low, then it goes up. As soon as the pulse is over, the current is still high for a while, but as soon as the filament is dissolved, it goes back to zero. And also this is an interesting feature that we can explore for computation. Now let's have a look at physically what happens, because also these devices, as you can see, are electrically tunable. So depending on which kind of pulse we apply, so on the voltage amplitude and the time width of the pulse, we can, for example, if we start from a reset state, we can create a small filament and then enlarge the filament. And this means increasing this conductance. Or in the other direction, we create a gap in the filament and then we increase the gap of the filament, thus decreasing the conductance. For the volatile devices, this doesn't happen. So the filament, we say, it self-disrupt. And depending on the current that we let through the device, we have a filament which is thinner or bigger. And this means that as soon as we stop applying the voltage, this device, this filament will take shorter time or longer time to self-dissolve. But another interesting property is that regardless the size of this filament, of course, whenever we want to switch the device on, the voltage that we need to apply is independent on the current that we let through it. And also this property, we'll see later, will be exploited for learning. But okay, let's start from some basic concepts so that everyone is on the same page. I will focus mainly on spiking neural networks and, as an example, on fully connected neural networks, because they are easy to understand, and spiking neural networks is actually the third generation of neural networks that exploits spikes. It means that we transmit information in form of spikes only when it is available. This has a very, very, very nice advantage. We do not need a clocked system. We can process data asynchronously, saving power again. So in a fully connected neural network, we have pre-neurons and post-neurons, and they are connected with artificial synapses, the same as we saw in a few slides before, but in a better graphical picture. These neurons can have several models. The simplest, but also nicely working one, is the integrate and fire neuron. So each neuron collects the information, the spikes from all the synapses, integrates the signal, and when this integrated signal is overcomes a threshold, this neuron will fire towards the next layers. This fire means something happened, I recognize something. An approach for efficient recognition in networks is, for example, using a wheel and tree call approach. This means that all these neurons here are competing among each other. Then one of them will fire, and it will say, oh yeah, it's me, I recognize, this is my topic to recognize. And it will prevent the others to fire. It's more or less like, stay quiet, it's my turn to shine. And how do we integrate it in a network, in a learning process? Well, we have several techniques. First of all, we have to understand if we want to do some offline learning, that means that we can train the network on our laptops, we do run a simulation and we train the network. We see which kind of configuration a network should have, and then we transfer it to our chip. And the task of our chip will be just inference, recognizing what's happening. Another option that is quite interesting on the edge, it's online learning, where training and inference occur together in the chip. But this is, of course, a bit more complicated, as you can imagine. And at the beginning, then you have to decide what to do, which approach, and then you have to decide which kind of learning. So I will just show you the main learning. First of all is supervised learning. So we have the data that are labeled. We have a teaching signal that teaches the network what to do. And the network learns. This is also a very good way of doing offline learning. Otherwise, we have an unsupervised learning, because where the data are not labeled, and the network has to learn itself how to cluster data. This is actually a good thing for online learning. Or we also have a powerful learning scheme that is reinforcement learning, where we have an agent, so our chip is interacting with the environment, is doing an action, and it's receiving a feedback from the environment. And depending on whether this feedback is a reward or a punishment, well, it will learn what it should or should not do. I will mainly focus on unsupervised learning, and I will show later some biologically plausible learning. But before I do that, let me just discuss classic learning scheme, for example, backpropagation. Because you might also know that backpropagation is the most powerful learning algorithm that we have now for artificial neural network. And it works like this. We propagate the signals in the layer of the network, and then we compute the error. So we see the signal that we obtain in the output, how different it is from the expected value. And then after we compute this error, we propagate this error back. And then we update the network parameters in order to minimize this error. This approach, it's powerful, very, 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 very powerful, but it has the very known problem of backward locking. So we cannot update before the signal is arrived to the output. And this means that for online learning, it's probably not the best choice. It's difficult. And moreover, I'm working on spiky neural network. If I want to port it in a spiky neural network, this is not really easy at all. Moreover, when we use this method of error minimization, we might get stuck in local minima. In this case, actually, noise that is usually something that we don't really trust too much, it could be beneficial because it could give us the kick that we need to escape this local minima. But okay, given these difficulties, well, maybe we can also have a look at something that happens in biology that might help us. And this is what it is called spike timing dependent plasticity. So when we have our neuron, our synapse, that is our memristive device, for example, and we have the neurons. So when the pre-neuron fires before the post neuron, it means that the conductance of the memristive device has to be increased because this firing is linked. And this is what we call potentiation, from low conductive state to high conductive state. Then, vice versa, if the post neuron fires before the pre-neuron, it means that there is no really link between the two. And this means that we have to decrease this conductance, thus leading to depression, where we move from high conductive state to low conductive state. And this rule was first observed in biology. And as you see, an interesting part of this rule is that depending on how far from each other in time these spikes are, we will have a higher or a lower change in this in the conductance of the device, or on the weight of the network. And this is actually one of the basic learning algorithms that we can use to implement our networks. But I want now also you to be patient with me and give me the possibility to have a look also at circuit level, what happens, how we can create synapses and neurons at circuit level. Because then we have to put them together to do this kind of learning. Let's start from FDJ. I told you that FDJ is the most most energy efficient memristive technologies. And therefore we can exploit it. But if we want to read it very nicely, and especially, okay, it's a two-terminal device. If we want to decouple program and read, well, we need to work with the circuit. So for example, we can use this kind of structure. In this kind of structure, we have an access transistor and a read transistor. So we can program the device using the access transistor. But then when we want to read the device, we pre-charge this node at a certain voltage. And then we disconnect this transistor and we let it evolve. And what we can see through the read transistor, since this FDJ can be modeled as an RC circuit with a high capacitance, what we see is that in time, this node will tend to discharge. But the time it takes to discharge will depend on the resistance of the FDJ. And as a consequence, the current which is flowing through the read transistor will change at time depending on the resistance of the FDJ. So if we let it evolve for, I don't know, 100 microseconds, well, then we'll monitor the current and we know what we stored in this FDJ. And this principle we can exploit, for example, to build synapses. Look at the synapses. We have two kinds of synapses. We have excitatory and inhibitory synapses. The excitatory one it facilitates the connection. The inhibitory has the opposite effect. Let's take this work from Erika Covi. We can, this work shows a differential synapse. And these two elements are resistive switching devices. We cannot apply the same one-to-one conversion if we change device. So if we change technology, for example, we can reproduce the same functionality using this 2T1C concept and using a differential pair here. What happens is that, let's assume that one device is in high resistive state and the other one is in low resistive state, because this synapse has to be programmed in a complementary way. So at first, we switch this word line on and we apply a voltage on the plate line and 0 to the ground to the bit line. And as a consequence, we switch this device. Then we do the opposite. We switch this word line off, switch this one on, and then we apply a voltage. And what happens is that this device switches in a high resistive state. Then at a certain point, we would like to read, right? Okay, we pre-charge the two nodes, N1 and N2. We apply a certain voltage to the plate line, and then we let these two nodes evolve. We switch the word lines off and see what happens. After a certain time, you will see that one node will charge faster than the other. And in this differential pair, it means that this branch will ask for more current than the other because it has a higher voltage here. But since the current is limited by this bias transistor, well, the current that we gain here will be subtracted by here. And in this way, we have a differential way of evolving of the current, and it's easier and faster to sense than, for example, the voltage, because you see here we have few millivolts, but here we have hundreds of nanoamps. The same principle can be used, for example, for an integrate and fire neuron. Programming goes the same, and the same concept is for reading. We have to apply a voltage and let it evolve. And what happens is that every time that we program this device, every time a spike comes to the neuron will start integrating, and this N1 will evolve faster and faster. And at a certain point, once we overcome a threshold, these circuits will generate the firing of the neuron. And I don't know if you remember, but before we said this is electrically tunable. So depending on the properties that we want from the neuron, so how many spikes we need before firing, we can explore the space of parameter and find the best condition to program this device. Okay, now that I show you an example of synapse and neuron, let's see how they work together in a system. In this case, we are using RAM, but the principle is the same. We have pre-neuron, post-neuron, synapse, and we apply an STDP protocol. What we do is basically showing an image on this fully collected neural network, and as you can see, the weight of synapses is evolving, and after a while, we will see the same kernel that we are showing exactly on the network. After the training, we test the network with different images, also with images with missing or pixel or with noise pixel. And if we perform learning properly, you see that anyway, we can correctly classify the image that we showed. This approach has a drawback. The main drawback is that these spikes here have to overlap. And only the overlap between the spikes generates a change in the synapse. As a consequence, we need long pulses, higher power consumption, and moreover, if two events occur in this time window, we cannot process them. And this is exactly where volatile devices come into play. Because thanks to volatile devices, as shown here, for example, where we use a synapse with a diffusive memristive device, a volatile device, as a non-volatile device, we can decouple the spikes and have two short spikes that span anyway in a quite wider time window. And again, you say, yeah, okay, this is a good simulation, but practically, have you ever tried? Well, my colleagues at Politecnico di Milano tried. They did a hardware using ARM, and they implemented the STDP for learning. And they have the synapses here, and then they used an Arduino to control everything. Now, look at this video, but before it starts, let me tell you, we will have two patterns, two lines, and they will start going around. They will start turning. And these two neurons will learn each one a different pattern, and these neurons will be able to follow the pattern. See, first we have that they learn a pattern, and then the pattern starts rotating, and they still are able to follow. And we have also some noise inside every now and then, so they are really robust. Anyway, STDP is powerful, but when we scale, it's not performing as well as we would like. So we have to slightly modify this kind of learning. And again, biology comes into play. For example, in these algorithms, there is the introduction of a calcium variable that is able to keep trace of the recent neural activity. And based on this recent neural activity, they can understand, the neurons can understand whether we want to potentiate, depress, or stay as we are. And again, here, the synaptic current is the one that determines the direction and the magnitude of the weight update. And in this system, we actually had a neuromorphic processor developed by the Institute of Neuroinformatics in Zurich, and we connected our memristor. It's not a co-integrated processor, so you need a big system. But still, what we can see is that, for example, the neuron behavior is resembling the membrane potential of a biological neuron, and our memristive synapse is able to change its weight, and it's able to, when it's potentiated, to trigger a lot of firing from the neuron, and when it's depressed, the firing rate of the neuron is less. I told you that reinforcement learning is powerful, and you can adapt STDP, for example, for this reinforcement learning. In this example, we have our small robot that goes around and has to find this square. And when it bumps, the square is a reward. And when it bumps on the walls, it's a penalty. And so, if you see, after a while, the neuron is the robot is able to map the space that it has around, and to have a clear representation of where to go to find the square, as you can see here, because the firing rate is higher here, which means that it was rewarded here. And if we look, well, in different experiments, if you increase the number of experiments, the robot learns faster. So the more it experiences, the more it learns. Another category of this learning that can be also used with STDP and modified, it's the error-triggered three-factor learning. And I really wanted to show this work by Erika, because they use ReRAM in vector matrix to perform vector matrix multiplication. So we have here a crossfire, and which is a very, very, very compact way of fabricating devices. And you can see that here they have a system which has a lot of amazing properties. It's asynchronous, and it needs only 8 transistors for the program circuitry. And believe me, it's not at all a lot, on the contrary. And moreover, since we have this compact structure, if we apply, for example, a voltage here on the columns and we read the current here on the rows, we already perform in one single step the reading and the integration, because this current will be the result of the sum of these currents. And so we accelerate the learning. Now, let me please go back to the volatile devices, and let's see what they can be useful for. An example is motion detection. So in biology, what happens is that we have several receptors that can react to movement in specific directions, as you can see here. And the core of this is that we have excitatory synapses and inhibitory synapses. Excitatory synapses have a positive current, and inhibitory synapses subtract this, have negative current. This means that when we have something that moves along this line, if the excitatory synapses are excited before we have a spike here. Otherwise, if we go in the other direction, and these ones are excited before the excitatory ones, we can see nothing. And this is the principle that we use for learning. Then we move then from this configuration to an electronic configuration where we have fast synapses and slow, and excitatory synapses and inhibitory synapses here. And in this case, it is important the physical configuration, where they are physically placed in space. And then we have a light bar that I hope is visible. Yes. And this light bar goes this direction. What happens is that the only part that reacts is the one, the east, where the excitatory synapses are excited before the inhibitory. Because all the others do not, the currents cancel out. If this bar goes back, well, we will have another situation. The west part will fire and will recognize the movement. And this can be done for all the orientation, and we can see that we have a quite good selectivity. Another thing that I wanted to show you about volatile devices is also that we can use them for decision making. So we have a beaver, and this beaver listens to two different sources, and it has to decide which one is the one that fires the most, that, for example, produces more sound. We can do this with a really simple system where we have input neurons, a certain number of synapses, and we will see what happens when we change the number. And then, depending on the evolution of the signal, we will have an output. Each synapse can be one or more ReRAM devices. And even in this case, we want to use volatile devices because we need to be able to forget after a certain point. Non-volatile devices, in this case, do not help. So after we apply a certain number of pulses from both sources, we can see that depending on the one who fired the most, the beaver is able to recognize, classify correctly the stimulus. But this depends actually on the feature of the network, on the retention time. If you remember here, we have different currents associated to different retention times. And this means that if we have a lot of stimuli in a long time, but we don't calibrate the retention time of the device accordingly, well, we won't be able to recognize anything. And still, and again, here, depending on the number of devices, since these devices are stochastic, if we put more of them in parallel, we see that putting more devices in parallel, we increase the performance, the accuracy in recognizing the correct input. But another thing that is really interesting for me is that if you remember, we said, depending on the switching voltage has a certain distribution. Depending on this distribution, we can tune the voltage so that we have a certain probability of switching this device on. And the interesting part is that in this kind of system, the lower is the probability of switching on, the higher is the accuracy, because here you see we have 1% and we almost recognize. But then here, when we have 70% switching probability, well, we don't recognize anything. And this is extremely nice because it means that we need less weight update. I mean, we need to stimulate, we need the device to change state with a very low probability. And this means we can save power. Well, okay, I'm at the end of the talk. And I hope that I convinced you that, well, we need new technologies because we have new paradigms to work with. And I hope I convinced you that memristive neurons and synapses can be a nice way to go. because they have nice properties that can reproduce cognitive computation. And this means that we can bring them also to the edge effectively, but only if we can develop them together with the devices, circuits, and algorithms, all together. And then I thank you for your attention. And if you have questions, I'm here.
So thank you very much, Erika, for this very nice talk. So if you have any questions for Erika, please do it as soon as possible using the chat channel. I see no questions for the moment.
I hope someone is still awake then.
Yeah. So, but I have one. What is the variability in the memristive devices?
Yeah, that's a very, very, very nice question. Thank you. Because it depends on the technologies. And if, for example, let's compare ferroelectric devices and ReRAM. Ferroelectric devices, if we have large devices, we have more domains and we can have more stochasticity. If we have very small devices, we expect that the stochasticity is less because we have less domain. But for example, for resistive switching devices, the filamentary ones that I showed you, it depends on the microscopical configuration of the device. And it means that we can have also 30% device-to-device variability or cycle-to-cycle variability. And our challenge is to have a network that can actually exploit this variability.
Thank you. So a question by Elias Ramos from Federal University of Rio Grande do Sul. He's saying nonlinearity is a property of the memory store and neural networks given the differential equations that model them.
Yes.
A differential equation may be unstable depending on initial conditions. Are there works involving device stability in this sense?
If I understood correctly, the question was about the stability of the device to see, depending on the initial condition of the device, if it can converge or not, right? And if yes, so the device is stochastic. So the idea would be to find a way to exploit this stochasticity to increase the stability of the system. And moreover, we can do it also from a point of view, from theoretical point of view, because, for example, there are learning algorithm studies in computational neuroscience that show that, for example, STDP can diverge, but if combined with a slower learning mechanism, and one example could be the calcium variable I showed before, we can achieve stability of the system.
Okay, thank you very much, Erika. But before closing, there is a question that arrived by Thiago Weber, also professor from Federal University of Rio Grande do Sul. In the case of offline learning, what are the challenges on modeling so you can work properly in a simulation training in a computer, or it's online learning the preferred way?
Well, in general, I think it depends on the kind of application. Depending on the application, we can choose if it's better offline learning or online learning. But from a simulation point of view, the first difficulty is having a good model that can really reproduce well the properties of the device, also in terms of device-to-device variability and cycle-to-cycle variability. And then the other really big challenge, and if someone knows how to solve it, please let me know, is that when we, the final objective of this neuromorphic chips with memristive devices is that we have the CMOS process, and then we want to fabricate the devices on the back end of line. This means that we will have some parasitics that are very, very, very difficult to estimate. And if we cannot estimate them well, it's difficult to predict how much the real network will be different with respect to the simulated network. And in some cases, this could mean that we can fail in the hardware.
Okay, so thank you very much, Erika.